Hi all! Just a quick couple of announcements at the top of the show. I find myself in an extraordinarily busy period of life, which includes some deadlines and some travelling, meaning that I haven't got as much free time to work on the show as usual. I still have some episodes backed up, but to avoid running out and to generally ease the pressure on my own personal life, we might skip releasing an episode for the odd week in the near future, but everything ought to be back to normal by the end of April. Also, you'll remember the 100th episode competition where you have to submit your answers to the questions "What is physics?" in writing or in audio form, for the chance of winning marvellous prizes and for the certainty of appearing on the show. Well, due to this busyness and also an overall lack of entries from you guys, I'm extending the deadline, which seems to be a very popular thing to do these days, and I think I'll extend that to the end of April as well. So please get those entries coming in. What is physics? And when I have enough entries, or in May, whichever comes sooner, I'll make that episode, award prizes to whoever entered, and declare that show the 100th episode, regardless of whether it is or not. After all, if theoretical physicists can renormalize to cancel unpleasant infinities, I can certainly declare an arbitrary integer to be 100. Alongside this, you'll notice that we are in the midst of a nuclear fusion series, and I am planning to break this up because, as you've probably noticed, we've got quite a long way to go until we get to the modern day nuclear fusion. So there will be some episodes on unrelated topics coming out in the middle of that series, just as a palate cleanser before we get back into the world of Tokamaks. Right, on with the show. Hello, and welcome back to Physical Attraction's series of episodes discussing the history, physics, and future of nuclear fusion. So far, we've discussed the history of fusion from the discovery of nuclei right up until the end of the 1950s. For fusion researchers in the West, this was a time of some disillusionment. The incredible progress in our understanding of nuclear physics, and our ability to harness the destructive power of these newly discovered fundamental forces, had led to hope that it might be possible to quickly develop a workable fusion reactor. Writing this show, and reflecting on the world, I'm always keenly aware of how unique this era of human history is. For thousands of years, the lives of proto-humans didn't change all that much. You could be in 30,000 BC or 20,000 BC, and notice only minor differences between those eras. In just the last 50 years, though, the world's population has more than doubled, and there have been incredible, unimaginable technological changes. James Gleick, in the book Time Travel, points out that this rate of technological change has given rise to a broad and popular conception of the future that rose alongside the early science fiction of people like H.G. Wells. Not just a future that was limited to next year's harvest, or personally growing old. Not just a future where the names and families of the monarchs and the borders of their dominions might change, but a future where technological advances and social changes could happen within our lifetimes even, that would lead to a substantially different world. Perhaps we are all aware of living in this special era of history, this era of unbelievably rapid change in so many different areas, and so our conception of the future is the more permanent, steady equilibrium. Change this rapid and vast in scale feels like it must have some ultimate destination, like it cannot continue forever. The centre cannot hold. Today we have debates, and of course we've had many of them on this show, about whether artificial intelligence will result in a substantially different world over the next few decades. There are wild utopian and dystopian visions where the world becomes an AI-enabled paradise or is else destroyed by a mal-programmed AI attempting to maximise the number of paperclips. I make this comparison not because the technologies are in any way similar. They aren't. But the common thread is the attitudes that we have towards them. Nuclear technology was briefly viewed in the same way and as the same panacea in the 1940s and 50s. The visions for what a workable fusion reactor would lead to were truly utopian, and perhaps they sound a little familiar to anyone who's read Ray Kurzweil or other enthusiastic futurists write about AI. Our generation lives between hell and utopia, for the very force that can destroy the human race can create wonders without end on Earth. It is small wonder that men's minds today shuttle between fears of doom and dreams of unprecedented bounty. Here are miracles within our reach, in medicine and science, production and power, possibilities so immense, so magical, that we can create a life on Earth more golden than man ever had dreamed possible before. Here is the utopian promise of the peacetime atom. If you just imagine that whole quote without the last sentence, you could almost imagine someone saying it about artificial intelligence today. But this was David Woodbury writing in his book Atoms for Peace in 1955. When Ronald Richter claimed to have developed fusion in Argentina, it was met with scepticism, but it inspired scientists in the West to take up the quest. Soon enough, with pinch devices and stellators, they felt they had several feasible designs that might one day realise nuclear fusion. But by the end of the 1950s, after some high-profile and embarrassing failures such as the Zeta project at Harwell, the authorities in charge of allocating funding became ever more sceptical that nuclear physicists could deliver on these utopian projects under budget and on time. On the physical side, each experiment, including those that were overhyped by the media as having finally cracked fusion, did show incremental improvements. The plasma was confined for longer, or it attained a higher temperature, or some or other instability was removed by the application of a new complexity in the magnetic field. But none of them were able to even approach what they were intended to do, ignite a self-sustaining fusion reaction that could produce more energy than it required to run. The neutrons that were produced by pinch devices such as Scylla and the Zeta project at Harwell were just from individual particles that were rapidly accelerated by electric and magnetic fields as the plasma confinement fell apart. Qualitatively, the process that produced them was basically the same as Rutherford's early bombardment experiments in 1984. It wasn't a route to sustainable fusion power. The ironic thing about the Zeta failure was that the embarrassment was caused due to these neutrons not coming from a genuine fusion reaction, but mere months later, a slightly modified machine did get neutrons from a genuine fusion reaction. Zeta was a Z-pinch machine. It generated its pinching, and hence the heat and pressure required for fusion, by driving a current down the spine of a tube and relying on the resultant Lorentz force to compress the plasma. The Scylla experiment in the US ran the current around the circumference of the plasma instead, a technique called theta pinch. A strong magnetic field then runs along the axis of the cylinder, and a compressing radial force results. Now these theta pinch machines, at least at first, turned out to be more resistant to instabilities. Remember Teller's vision of plasma instabilities as like a series of rubber bands trying to confine jelly, which squeezes out through the gaps? This alleviates that problem slightly due to something called Alfvén's theorem. When we imagine lines of the magnetic field, or lines of magnetic flux as they're called, Alfvén noted that they tended to be frozen into a plasma or fluid that contained them. In other words, the plasma likes to rearrange itself to preserve any magnetic field that's inside it. When you use a theta pinch device, the magnetic field lines are right down the spine of the tube of plasma, frozen in, and consequently it's better for certain kinds of instability, because the plasma wants to rearrange itself to keep that field in place. Now this allowed for theta pinch devices to heat deuterium to 10 million degrees Kelvin and produce all of the expected products of thermonuclear fusion. In 1958 they had effectively succeeded where Zeta had failed, but it didn't seem to matter. Even though genuine neutrons from thermonuclear reactions were being produced, the theory had now moved on. Everyone was now thinking about Lawson's criterion. You remember this. The product of density, confinement time, and temperature have to be high enough to produce net power. Now the pinch experiment didn't seem capable of confining the plasma for very long before instabilities tore it apart. So even though they were now reaching the kind of densities and temperatures that might be feasible with fusion, getting the confinement time as well was very difficult. These instabilities were an immense headache. They weren't entirely understood theoretically, and they were very unpredictable experimentally. To give you an idea of how complicated plasma instabilities can be, I should of course point out that there is still substantial research going on into plasma instabilities 60 years later, with all the time and effort and intellectual endeavour that's gone into plasma physics and fusion research, all of the computing power that we have now that they didn't have then, all of the theories that have been developed, and all of the experiments that have taken place in the various fusion reactors across the world, and there are still unsolved and perhaps unsolvable problems associated with turbulence and instabilities. One of the fundamental issues here was that, at the start of the fusion research, there was a misconception about how plasmas can be treated. Remember when we described the stellarator and pinch concepts as charged particles being bent around on orbits or forced inwards according to simple applications of Maxwell's laws and the Lorentz force? Well, this is really just assuming that a plasma can be treated as a sort of cloud, a collection of charged particles, something closer to a gas. But in reality, it is the fourth state of matter for a reason. It behaves differently, more like a fluid, the many individual charged particles, and you need a full magnetohydrodynamical theory to understand it. The influence between the charged particles is very important. Collective motions of the plasma can produce propagating and decaying waves of motion, of particles, of electric field, of magnetic field, all kinds of waves. Instabilities can even go beyond the realms of ideal magnetohydrodynamic theories, and with no theory to guide the experimenters, they were at a loss as to how to correct some of these problems. This is what can happen when you attempt to force a complex system with many components that all interact with each other to do whatever you want it to do. Take running the current through the plasma to cause it to pinch. You succeed in your primary aim, to compress the plasma and heat it up, but you also get unwanted secondary and tertiary effects, with the plasma pinching in multiple locations and forming many small links, a chain of linked blobs of plasma called the sausage instability, after the chain of sausages that the physicists thought that it resembled. Every way physicists seemed to attempt to manipulate plasma, it led to these secondary effects, and most of them turned out to be self-reinforcing. They grew rapidly, and ultimately destabilized the plasma before a self-sustaining reaction could get going. Just the fact that you had a small flash-in-the-pan thermonuclear reaction going, this did nothing to change the fundamental plasma physics. It certainly didn't help matters. Charles Safer, in his wonderful book The Sun in a Bottle, puts it well. He said, quote, "Physicists built bigger and more expensive machines to attempt to wrestle the plasma into submission, but they were just uncovering more and more subtle ways that the plasma fought against their will." Quoting from Joan Lisa Bromberg's book on fusion, "The belief that a reactor would follow thermonuclear neutrons by a short interval was fading. In its place, Livermore's opinion was beginning to represent the view of a growing number. It should be recalled that the function of a magnetic bottle is just precisely the long-time confinement of the plasma, not the achievement of fusion reactions. Even if 100 million degree plasmas were eventually produced by means of pinch experiments, the failure to achieve long-time confinement in a device of reasonable size would eliminate the pinch as a fusion reactor scheme. Confinement, that is, stability, and not neutrons, the evidence of thermonuclear reactions, was becoming the key issue." Okay, so much for the pinch experiments. But what about Lyman Spitzer's brilliant ski-lift brainwave, the figure-of-8 stellarator with its complex, twisty magnetic field? Here the whole point was confinement, attempting to contain a hot plasma with a complex magnetic field arrangement first and foremost, as you bring it up to a controlled burn, rather than rudely and rapidly pinching it into instability and disintegration. Was this approach working better in the 1950s? In a word, no. Plasma suffered from problems in the stellarator too. It could achieve higher temperatures, but physicists saw micro-instabilities, particles from the plasma being dumped onto the walls due to small local perturbations. A slight difference in density or temperature throughout the plasma expanded rapidly and threw particles against the walls. This reduced the density and it took heat out of the system via the kinetic energy of the particles. Since the whole point was to confine a hot, dense plasma, these micro-instabilities, which resulted in the loss of particles and the loss of energy, were disastrous for the fusion project. The hotter the plasma got, the faster the particles were lost. A vicious cycle. It was believed early on that the loss rate should be possible to reduce quite rapidly just by increasing the magnetic field strength used to confine the plasmas. The initial theory suggested that the loss rate would scale with the inverse square of the magnetic field strength. In other words, double the magnetic field strength, and the loss rate is cut by a factor of a quarter. And this means that you can basically just jack up the magnetic field until your loss rate is acceptable. But these dramatic improvements failed to happen. Even as successively larger machines delivered better magnetic fields, the particle loss rates didn't drop anywhere near as quickly as the theory had predicted. Confinement times weren't improving, and after a fraction of a second, the particles would still spiral out of control, making sustained fusion impossible. In the early days, Spitzer's optimism had carried the day. He hoped that at 1 million degrees Kelvin the ionization of hydrogen should be complete, and the plasma may be regarded as an assembly of free charged particles. The phenomena should follow simple scaling laws. Observations at 1 million degrees should allow for accurate prediction at 100 million degrees. But he was wrong about the plasma physics in the early 1950s. Plasma was far more complicated. And he was wrong about the scaling laws. You could not extrapolate plasma's behaviour simply to higher temperatures. Every new frontier in temperature and density brought new behaviours and new instabilities. This increasing despondency was reflected in how Spitzer described his own stellarators. The Model A and Model B were research experiments. The first was to prove that plasma of 1,000,000 degrees could be created. The second would prove that it could be confined for long enough to characterise its behaviour. Once that was done, the Model C would, at least in theory, heat the plasma to self-sustaining fusion reaction temperatures. The Model C was supposed to be partly a research facility, partly as a pilot plant for a full-scale reactor. Bear in mind that this is what people say ITER, the big tokamak being constructed in the south of France, is today. He had initially expected to have a working fusion reactor within sight by the end of the 1950s. Instead, the $24 million Model C was now described as, quote, entirely a research facility without any regard for the problems of a prototype, end quote. And, according to Safer, when it first came online, the only reason it was better than its predecessors was because it was physically bigger, which meant that the particles took a longer time to actually crash into a wall. Things weren't looking too promising for the Stellarator to produce sustained fusion anytime soon. A profound pessimism settled over the fusion community around this time, with the late 1950s and early 1960s known as the Doldrums in fusion research. By the time the early 1960s came around, gone were the glory days when fusion scientists, at least in the West, could get 3 alternative approaches funded with little difficulty. Many were struggling for the survival of their research groups, and they faced new competition from new generations of nuclear fission reactor, the fast breeder concepts. In nuclear fission, funding bodies saw a technology that had already been proved to work, and that was already generating profit for private companies. Fusion, on the other hand, promised a great deal and had not yet delivered. It seemed that the fusion researchers had been immensely over-optimistic in their speculations that fusion would be possible within a decade. We've discussed part of why already, the incredible pace of development in physics and in nuclear technology in that era. But Joan Lisa Bromberg makes an excellent point in her book. She wrote, quote, there was the post-war exuberance over the possibilities of technology, but there was also no one in 1952 who commanded all of the bits and pieces of scientific and engineering knowledge required to make fusion generators. The disciplines of fusion physics and fusion engineering did not exist. There were astrophysicists like Spitzer, who knew about the rare cold plasmas of interstellar space. There were accelerator specialists like Tuck and Wilson, who understood the careful design of magnetic fields and power supplies to manipulate the trajectories of charged particles. There were cosmic ray scientists who had studied the behaviour of charged particles in magnetic fields at extremely high energies. There were even weapons physicists who could contribute some rudimentary methods for measuring the rapid plasmas. But no one had an overview. The discipline of the nuclear engineer did not exist. Constructing a working fusion reactor, in other words, would require a fusion of different disciplines in its complexity. Everyone could only see their own part of the whole. The result was that the optimistic predictions fell flat, and those in control of the purse strings, especially in the US, were losing patience. He said, is this not a very expensive way to get this basic knowledge? We can build these machines until the cows come home. I am wondering in my own mind, how long do you have to beat a dead horse over the head to know that he's dead? Said Senator John Pastor on the Appropriations Committee back in 1964. To understand what woke the research community from its depression, we need to return once more on this show to the Soviet Union. It was known in the West that the Russians were working on a nuclear fusion project. In 1956, for example, Igor Kurkatov, one of the scientists we mentioned in the episodes on the hydrogen bomb, came to the US and gave an astonishingly open talk for the Cold War that described their efforts to build something like a fast-pinch fusion reactor. In many ways, this dramatic speech was an olive branch to the physics community on the other side of the Iron Curtain. The Soviets were not only confirming the fact that they had a fusion program, but they were divulging genuinely useful details about how it worked and the ideas that they had. It was arguably the first instance of truly international collaboration on a fusion project. There were occasional subtle hints on the rare occasions when Soviet scientists did visit the West about the progress of this project. While Edward Teller is a perfect example from history to demonstrate that not all scientists are apolitical, the dream of fusion power can be quite international in nature, about lifting the species as a whole up, in the same way as harnessing fire did. Equally, the scientists were frustrated that the usual process of collaboration, where people try to work together and avoid duplicating the same results, were being frustrated by politics. An example of this arose a few months after Kurchatov's speech, when the designer of the Tokamak, Lev Artesimovich, went to a conference in Stockholm. The conference was about astrophysics, but at the informal dinner afterwards, Artesimovich dropped hints. He was making some comments about how he and I were doing similar things to each other under the wraps of secrecy, and proposed a toast to plasmas. May they be worthy of the trust placed in them by theorists, Spitzer later recalled. The implication, of course, was that the Russians had also struggled with plasma instabilities and confinement, and were starting to run into the same issues as scientists in the West, when their nice simple theories of plasma just didn't match up to the experimental reality. In 1958 there was a conference in Geneva with Soviet attendance where lots of fusion material was declassified. The Soviets at least appeared to be at a similar stage to the US at this point. They had pinch experiments that could produce neutrons, but there was still some uncertainty about whether or not they were thermonuclear in origin, and this was at any rate still an unknown distance from a working reactor. But in the wild imagines of the defence-minded scientists at Los Alamos, the Russians could have had anything. Giant magnetic mirrors, mass-produced fusion reactors. Perhaps they had come up with some alternative reactor design that was superior to anything the West had even thought of. Well, as a matter of fact, they had. And like many pieces of science history, its own little mythology has developed. Now it's worth pointing out that there is a more mundane version of this history reported where the idea comes from Sakharov, the genius mentioned several times in our episodes on the bomb project in Russia. But this is the story that Soviet physicists tell each other, and so it's the one that I will tell you. The story starts with a man called Oleg Lavrentiev. His father was a clerk, his mother was a nurse. He volunteered for the front lines during the Great Patriotic War, known to us as World War II, and after fighting the Nazis, ended up stationed on the island of Sakhalin. To call this a bit of a backwater is an understatement. It's the island off the far east of Russia, just north of Japan. Seriously, it's there, it's bigger than Sri Lanka, but aside from being disputed between Japan and Russia, it hasn't always been pivotal in world history. It's there that Oleg had plenty of time to study a subject that he'd been fascinated with first in school, nuclear physics, and he wrote directly to Stalin with some suggestions. The letter to Stalin naturally didn't get anywhere, although listeners to our sister podcast, and when we've had episodes on this show, which has extensively covered the life of Stalin, will know that he wasn't averse to answering letters even to old grandmothers with cows. But another letter to the Central Committee of the Communist Party was identified by someone as more than the ramblings of some crackpot. Oleg was onto something. According to ITER's website, quote, what Junior Sergeant Lavrentiev had devised in his remote posting were the blueprints of an H-bomb and the concept to produce energy through controlled thermonuclear reactions. So Lavrentiev was immediately taken off latrine cleaning duty or whatever else one gets up to on Sakhalin, and given a private room and all the resources he needed to expand on his ideas. His paper eventually found its way to Andrei Sakharov, who wrote, I think we need a detailed discussion of Comrade Lavrentiev's draft proposal. Regardless of the outcome of the discussion, now is the time to note the creative initiative of the author. The obscure sergeant with no formal training in a nuclear physics hobby had sparked the Soviet H-bomb project and the Soviet nuclear fusion project. At least, so the story goes. He left the army and quietly laboured at the Kharkov Institute of Physics, working on nuclear-related problems right up until he died in 2011. It was only in 2001 that all of this information was declassified and published in a Russian physics journal, and the remarkable story of the genesis of Soviet fusion became public. Loyal listeners will remember Sakharov from our episodes about the Soviet atomic bomb project. In those secret cities, the Atomgrads, where the Soviets worked on the properties of thermonuclear weapons, Sakharov was one of the people who enabled them to catch up to the Manhattan Project and in some areas overtake it. Like many scientists who worked on the atomic bomb, he felt the weight of moral responsibility. He said, quote, thousands of years ago, human tribes went through a fierce survival test, and in this competition, it was not only important to be good at wielding a stick, but also to be able to think, preserve traditions, and selflessly help fellow tribe members. Today, humanity is going through the same test. He later became a fierce and staunch advocate for human rights and a critic of the Soviet regime, winning the Nobel Peace Prize for his political efforts. He wrote, at first I thought, despite everything I saw with my own eyes, that the Soviet state was a breakthrough into the future, a kind of prototype for all countries. Then I came to the theory of symmetry. All governments and regimes to a first approximation are bad, all peoples are oppressed, and all are threatened by common dangers. Sakharov came up with many of the same ideas as Edward Teller in parallel during the development of the fusion bomb. Yet also, as early as 1950, around the same time that Ronald Richter was making his wild promises to Juan Perón, Sakharov was thinking about magnetic confinement fusion, a controlled reaction for the production of energy. Fortunately for history, his design was broadly different to those pursued in the West. So far we've discussed two types of fusion design overall. The pinch machines ram a current through plasma which compresses it, ideally, hopefully, causing it to fuse. But in practice, plasmas produced this way tended to succumb very quickly to instabilities, with not much hope of getting out more energy than you put in. Meanwhile, the stellators use an arrangement of magnetic fields to attempt to confine the plasmas for a very long time. Rather than crushing the plasma, squeezing it into oblivion, the stellators attempt to hold on to it. But the stellator scientists in this era were seeing individual particles diffuse outwards and hit the walls far faster than they had anticipated. Both were attempting to satisfy this Lawson criterion, the idea of this triple product of density, temperature, and confinement time. Stellators were good at getting higher confinement times, but they suffered from this diffusion, and the density and heat tended to dissipate. Pinch machines could produce all the density and temperature you wanted, but instabilities rapidly caused the crushed plasma to fall apart or radiate its energy away. Sakharov's idea used a donut-shaped torus with coils of wire that induced magnetic fields to establish a loose hold on the plasma. This is a little like the stellator. But another set of coils used fluctuating magnetic fields to induce a current inside the plasma, much like the pinch machine. In a way, then, this device is something like a combination of the pinch machines and the stellators. A current is driven through the plasma that heats it and crushes it down to a lower density, while the coils of the device also act to confine the plasma for a longer time. The device was called the Toroidalnara Kamera I Magnetaya Katushka, or Tokamak for short. And yes, I will be using the shortened version. The plasma current required to confine the plasma for any length of time, by acting to prevent it from diffusing outwards like it would in the stellator, used this pinch mechanism. But the plasma current also makes the behaviour of the plasma more complex. And, if the plasma current is ever interrupted, for example if there are gaps in the plasma that prevent it from conducting or something like that, then the plasma is flung out in all directions. These events, known as disruptions, can occur when magnetohydrodynamical instabilities prevent the current from flowing coherently through the plasma. Now, since the current is doing a great deal of work confining the Tokamaks plasma, this disruption can be an extremely violent event and can even damage the tokamak itself. To quote a paper about the upcoming device, ITER, a lot of energy ends up in the wrong places when a disruption occurs and plasma is shot in all directions. According to SAFER, one disruption at the JET experiment in Oxford, the world's largest currently operating tokamak if I'm right, caused the entire device to jump a centimetre into the air. Other recent papers have suggested that, if major disruptions occurred in the new tokamak ITER, they could either destroy the machine or render it non-operational for months. In fact, according to some people, the real mission of ITER is to demonstrate a disruption control system that studies and shows the tokamak, and modern engineering, can deal with the consequences of a big disruption with the huge currents and plasma energies that might be required to produce this net power. Now, there are various different types of methods trying to deal with disruptions, including putting large amounts of shielding on the internal components of the tokamak to mitigate the damage that they cause, or adjusting magnetic fields subtly to prevent them entirely. Ultimately, though, it looks like a combination of both would be required for a really successful fusion power plant. Even after years of operating some of the experimental tokamaks, around 10% of runs result in disruption, so it may be the case that fusion engineers and scientists have to learn to live with them, diagnose them, and combat them as they happen. After all, they must have run through so many different parameter sets by now in the runs that they've done to see if they can minimise disruptions. Now, this is very controversial, and there's always what you might call some fusion politics to negotiate whenever you read anything about any type of fusion proposed by anyone. Everyone has a favourite design, and pretty good reasons for having a favourite design. But if it is the case that there's some non-zero probability of your entire power plant breaking down for 2 months, or needing a complete rebuild due to a disruption event, it's obviously a concern for people designing tokamaks today, and for the design ever to be viable at all, as a real working power plant that's not just being used for experiments. But we'll return to all of this later. For now, for us, the tokamak is just an idea in Sakharov's head. Next episode, though, we'll talk about the early Soviet experiments with the tokamak, the eventual and remarkable trip by Western physicists to the USSR at the height of the Cold War to look at their research, and the Tokamak Revolution. Meanwhile, one of the new diagnostic instruments that those scientists took with them to assess what progress had been made with the tokamak would have its own unique place in fusion history. They had a laser. Thanks for listening to this episode of Physical Attraction. All of the usual caveats apply. You can listen to all of our past episodes on iTunes, wherever you get your shows. You can find them on www.physicspodcast.com, where you'll also find a contact form where you can bombard us with any questions, comments or concerns. Nice feedback is always appreciated. I do sometimes get it. And you can do the same, of course, by reviewing us in a public forum on iTunes, on Stitcher, wherever you listen to your podcasts. That's all very good. Of course, the best thing you can do to support the show, if you don't want to make a donation, which is also an option, is to tell as many people as possible to listen to it. Until next time, then, take care of each other.
Okay.